In this video, we look at how computers store real numbers, or fractions. Let's consider three examples of typical floating point numbers. So in the first example, we've got 0, 0, 1, 0, 0 stored in the mantissa, and 0, 1, 0 stored in the exponent. So we know that the exponent is 2, and that means move the binary point 2 places to the right, so that's 1, 2, the binary point stops there. So let's redraw the number and see what we've got. 0, 0, 1, 0.00. Okay, so this is worth a half, this is worth a quarter, this is worth 1, this is worth 2, and this would be worth -4. So here we've got the number 1. Let's look at the second example. So here we've got 0, 0, 0, 1, 0 in the mantissa and 0, 1, 1 in the exponent. So if we look at the exponent, we've got 2 plus 1, that's 3. That means move the binary point 3 places to the right. So 1, 2, 3. And the binary point stops here. So let's redraw the number out. 0, 0, 0, 1. There's our binary point. 0. Okay, so this is a half. This is 1. This is 2. This is 4. This is -8. So here we've got the number 1. Let's look at the third example. Here we've got 0, 1, 0, 0, 0 in the mantissa and 0, 0, 1 in the exponent. Okay, so the exponent is 1. That means that we've got to move the binary point 1 place to the right, so it goes to here. Let's draw that number out again. 0, 1, followed by our binary point. 0, 0, 0. Okay, so this time this is representing a half, this is representing a quarter, this is representing an eighth, this is representing a 1, and this is representing -2. So here we've got the number 1. So this is a bit surprising. Here we've got three numbers that all equal 1. That's a 1, that's a 1, that's a 1. So three different ways of representing the number 1. Now in reality, there's an infinite number of ways of representing 1, but depending on the number of bits you've got for the mantissa and the exponent, will of course limit the number of possible combinations. But there is more than one combination for representing the number 1, and that's not right. We need a much more uniform way of representing numbers. So there's only one way of representing any given number. And so what we do is we normalise the number. And one of the advantages of normalising the number is that we make sure we're storing the number with the greatest accuracy possible. So which of these representations of the number 1 is correct? Well, actually that's quite an easy one to answer, because if you've got a positive number, then the number should always start 0, 1. If you've got a negative number, then the number should always start 1, 0. And then you know that the number is normalised. So if we look at the three examples that we've got, there is only one example where the number starts 0, 1, and that's the third example. So the third example is actually the correct representation of the number 1 in 8 bits. It's said to be normalised. So let's run through a few examples. So if we start with 6.5 that we were looking at in a previous video, we've got 0, 0, 1, 1, 0, 1, 0, 0. So this is the number 6.5, but it's not normalised. So what we need to do is make sure that we can move the binary point over to here, and then our number will start 0, 1 rather than starting 0, 0. So if we're going to move the binary point 3 places to the left, to get it back to its original position, we would have to move it 3 places to the right. So when we store our exponent, we're going to want to store the number 3. And then our mantissa is simply our number, remembering of course that it starts 0, 1. So we've got 0, 1, 1, 0, 1. And this is now the correct representation for 6.5. Let's just quickly run it back through and check we're okay. So our exponent is 2 plus 1, which is 3. That means move the binary point 3 places to the right. So if I was going to do that, I'd go 1, 2, 3. And we can see that that would then represent a half. That would then represent 2. That would represent 4. So we've got 4 plus 2 plus a half is 6.5. So we're good. Okay, let's have a look at 2 1/4. So that's 0, 0, 0, 1, 0, 0, 1, 0. So this is 2 1/4. But it's not normalised. We need to move our binary point to here. So the number starts 0, 1. So we're going to store 2 in our exponent. And then we're going to store our number in the mantissa 0, 1, 0, 0, 1. So let's run it back through, check we're okay. So we've got 2 in the exponent, which means that we would want to be moving the binary point back to here. And if we did, we could see that that would be 1/4, and this would be 2, so 2 1/4. Okay, let's have a look at a more tricky number now. Let's have a look at minus 2 1/2. So the way to do this is to just put the number 2 1/2 first, the positive 2 1/2. So if we did that, we'd have 0, 0, 0, 1, 0, 1, 0, 0. Okay, and now we've got to convert that into a negative number. Stored in 2's complement, a couple of ways of doing this, but in essence what you get is 1, 1, 1, 0, 1, 1, 0, 0. So this is minus 2 1/2, but it's not normalised. We need to move our binary point from here to here, because remember, negative numbers start 1, 0, and these bits aren't really significant. So we're going to be moving our binary point back 2 places. So we're going to store the number 2 in our exponent, and then in our mantissa we're going to store our number, which has to start 1, 0. So 1, 0, 1, 1, 0. Okay, let's run that back through. So we've got 2 in the exponent, which would mean that we'd be moving our binary point 1, 2 places there. If we did that, this would be worth a half, this would be worth 1, this would be worth 2, and this is minus 4. So we've got minus 4 plus 1 is minus 3, plus a half is minus 2.5. Okay, let's finish by looking at a very tricky example. So here we've got minus 0.25, minus 1/4. So if we write that out as a positive number to start with, just because it's a little bit easier, 0, 0, 0, 0, 0, 0, 1, 0. Okay, and 2's complement then, working back the other way, we've got 0, 1, 1, 1, 1, 1, 1, 1. So this is minus 0.25, but it's not normalised. We need to move our binary point, which is here, over to here, so that the number can start 1, 0. So we're going to be moving our binary point back to the left when we convert the number back. So 2 places to the left, we're going to have to store our exponent as a negative number, minus 2. So that's a minus 4 plus a 2 is minus 2. And now with our mantissa, we can write out our number, which is going to be 1, 0. Remember, it always starts 1, 0 if it's negative. 0, 0, 0. So we've backfilled a few zeros here. It doesn't matter, it's not significant. Okay, so if we're going to convert this number back out again to check that we're correct, let's have a look at it on the number line. So to make it easy to see the illustration, I'm going to put my 1 binary point 0 just here on the number line, and then we had 3 zeros here. Now, to move the binary point 2 places to the left, because my exponent is minus 2, I'm going to have to move it 1, 2 places to here, and it's kind of in the middle of nowhere really. So what we're going to do is put some 1s in here, because the number started with a 1. You could put 1s over here too. They're not significant. It doesn't really make any difference. Okay, so where are we? Back out on the number line. This is representing -1. This is representing a half. And this is representing a quarter. And don't worry about these bits here. They were just for illustrative purposes. Okay, so we've got -1 plus a half plus a quarter equals minus a quarter, minus 0.25.